Hi, class. Today we'll be covering Chapter 17, Integrating Network Devices. This is a fairly short chapter, but I think you guys will enjoy it anyway. These are our main objectives: explain Internet of Things, describe unified communication features and functions. We are also going to describe the functions and major components of ICS and SCADA networks. Internet of Things. If you get online and try to find a definition or an explanation of what exactly that is, they're kind of all over the place, but I think this one from Cisco is pretty close to about as accurate and simple and clear of a definition as I could find. So I'm going to go ahead and run through that real quick. IoT, the Internet of Things, connects ordinary objects to other objects and applications in the cloud, making them intelligent and interactive. So that is the Cisco kind of textbook definition. So in general, we're talking about a huge variety of devices that can be accessed and controlled via the internet. These are often devices that can connect directly to internet resources. And one other note: this doesn't apply to personal computers, routers, or servers. So we're not talking about the kind of typical network capable devices. We'll go into a little more detail on what counts or what we're generally talking about when we talk about Internet of Things, but we're usually talking about standard kind of household devices like refrigerators, locks, light switches, all of those kind of things, and we're adding some sort of network capability and smart functionality to them that allows them to interact with other devices or be managed remotely or interact with some kind of cloud online service. One of the nicer aspects of some of the IoT devices is they are capable and sort of built around the idea of automation. Not all of them, but very frequently it's the case that automation is a fundamental aspect of how they work. So you can have things like smart bulbs, smart refrigerators, smart thermostats. There are a number of systems that are built to integrate with these kind of things, like the Amazon Echo, integrated home audio systems, smart speakers, etc. So you can set up automated processes like your light bulbs will dim in the evening, or they will turn on in the morning, or light switches that will automatically turn on or dim depending on the time of day, thermostats that will maybe it's cold in the morning, and so you want to crank up the heater a little bit when you go to get out of bed, take your shower, and make your breakfast. So you can set up smart thermostats that will have a routine where they automatically kind of carry out these actions. So some of it can definitely increase levels of comfort and convenience when set up properly. This is just a screenshot of a smart thermostat. For the most part, it may not look too much different than a regular thermostat, and for a lot of people that's kind of a plus. You may have some extra menus or some options in there, but for the most part, at a glance, oftentimes these smart devices will look indistinguishable from regular devices. Not in every case, but frequently enough. One nice aspect of IoT devices is since they can access the internet, they can usually access different resources or databases that are available online, where you have certain devices like Amazon Alexa, or becoming more popular now is smarter AI devices or AI assistants that can access resources online and pull information for you. You can also have things like smart printers or multifunction devices. They essentially have the functionality of multiple devices built into one. These devices are increasingly having the ability to connect to the internet and enable more efficient communication. Another example that would be more related to physical access control type device or physical security type device is something like a smart garage door opener or smart door locks, that sort of thing. So this has a number of advantages. Rather than just a button that's available on your car to open a garage door when you pull up to the house, you can usually access these things remotely, either via an app on your phone or some sort of web interface. And so if you have company coming over and you're not available, you can let them in remotely. If you have someone delivering a package that's something more expensive, you can open the garage door and allow the sort of FedEx, UPS driver, or mail service provider to put that package in your garage rather than leaving it out on the front door. There's definitely a number of advantages to this type of technology. A smart garage door would be an example of a physical access control device. Some of these IoT devices make setting up and monitoring a robust home security system very simple. Examples would be like the Ring systems from Amazon. Generally, with these devices, you get the normal functionality of a doorbell, plus you get a camera that's usually, rather than a standalone or closed-in system, you can usually access these camera feeds remotely. They often come with built-in speakers or microphones that can also, in addition, be accessed remotely as well. You could potentially encounter a number of challenges while trying to set up IoT communication technologies in a home environment. So one of the issues is the kind of general layout. If you compare a home environment to maybe a typical sort of office farm, the office farms typically have wider open rooms with multiple cubicles, and it's a little easier for a wireless access point to send its signal as far and as wide as it possibly can. In a home environment, you tend to have smaller rooms, hallways, corridors, laundry rooms, all kinds of just a more complicated layout, and sometimes that can make it harder for signals to reach all of the devices in an entire home network. There are quite a few protocols that support mesh networks for low-powered devices or just IoT devices in general. Zigbee is an open source protocol, supports over 64,000 devices. It operates at the 2.4 gigahertz or the 915 megahertz band. Z-Wave is a proprietary protocol. It supports 232 devices. It operates at the 908 megahertz to the 916 megahertz band. Wi-Fi is certainly a key aspect involved in IoT communication. Often, though, not every single device on the network will communicate to or use Wi-Fi or communicate over the internet directly. Oftentimes, the layout or the network structure will have one base station that is connected to Wi-Fi and communicates out over the internet. The other devices will use some of the other protocols and create a mesh network, and they'll coordinate with the base station anytime they need to access internet resource. That isn't the only structure or option available for IoT devices, but it is often a kind of network topology or network layout that you'll encounter. We talked about Wi-Fi 6 previously and how one of the major advantages of Wi-Fi 6 is that it's capable of handling communication from many devices much more efficiently than previous versions of Wi-Fi. And so we can see how that will be greatly beneficial towards IoT devices or supporting IoT devices. Bluetooth is also an option available for communication for IoT devices or wireless networking. What is Bluetooth? Again, it is a wireless networking protocol developed to simplify connections between devices. Whenever we connect using Bluetooth, we create a personal area network, a PAN. Connected Bluetooth devices. Security concerns apply to all the devices in communication within a PAN. So our normal security concerns still are a critical aspect when we're talking about personal area network. There are two main security tools that we use to help secure Bluetooth devices. One is that we have the ability to make them invisible, or more specifically, Bluetooth devices are not visible unless they are manually set to a discovery or discoverable mode. So that is one security tool available. The other is that we have a PIN, a personal identification number, that is required to pair a device. So we have a PIN that is required to pair a device. That is the second tool available. And this is just a screenshot from a device showing the option to toggle Bluetooth from a discovery mode or to a non-discoverable mode. There are two different technologies that are relevant when we're talking about Bluetooth. One is the older version of Bluetooth. You'll sometimes hear this referred to as Classic Bluetooth or Bluetooth Classic. This is the older standard that had greater range and greater speeds. Generally speaking, greater ranges and greater speeds. That's counterintuitive, so I'm going to say that again. The older version of Bluetooth had greater range and greater speeds, generally speaking. The trade-off was that it used a lot of power to run. And some devices, we generally want them for the sake of battery life or other aspects, other reasons, we may need a lower powered option to be more efficient. So we have this newer technology called BLE, Bluetooth Low Energy. This was introduced in Bluetooth 4.0. It's still used in Bluetooth 5.0. It operates at the same 2.4 gigahertz radio frequency. One important note is it uses different modulation. So these two technologies are not interchangeable. Often devices that are built to use the old Bluetooth technology cannot connect with the new ones, and devices that are built around the new Bluetooth technology cannot connect with older devices. You have some exceptions where smartphones are generally designed in a way where they can connect either version, so older Bluetooth devices or the newer BLE devices. Hardening of IoT devices. The goal of IoT device hardening is to decrease the danger of loss or downtime, increase the protection of personal information and company data, and keep devices or software firmware up to date and protect against physical security threats. Hardening IoT devices. This is just an example of some steps you may want to take to protect, for example, security cameras that are using IoT technology. Obviously, you would like to limit physical access to the cameras. Place all cameras inside their own SSID. Put all the camera feeds on their own VLAN. Use a very long pre-shared key, a PSK. Set up routine queries for camera firmware updates from the manufacturer, and use a access control list to determine access. Okay, that covers the key aspects of IoT devices that we're going to cover in this chapter. Next, we're going to talk about unified communications. TCP IP-based communication replaced the traditional PBX style phone systems. VoIP, or Voice over Internet Protocol, enables communication over an IP network. Unified communication. This includes things like voice, video, and messaging. The general idea behind unified communication is we're just combining all methods of communication or multiple methods of communication into a single service or platform. Early VoIP systems separated data and VoIP. It required multiple cables running to each drop, but it wasn't really necessary. There was no sort of hard and fast rule or strict reason why you had to separate the two technologies. Here are some key VoIP system protocols that we are going to need to memorize. Real-time Transport Protocol, RTP. Real-time Transport Protocol, RTP, uses UDP and doesn't have a hard fast port. IETF recommends ports 6,970 to 6,999. But there's no dedicated or officially assigned port for RTP, at least the last I checked. The other key protocol that we're going to want to remember is SIP, Session Initiation Protocol, SIP, uses TCP or UDP ports 5060 and 5061, uses 5061 for encrypted traffic over TLS. Unified communication features, various services added to the classic VoIP, presence information, video conferencing and real-time video, fax, messaging, collaboration tools, and workflow. We'll cover presence information really quick. For the most part, this isn't a super complex topic. If you guys have used any kind of social media platforms or online communication platforms, something like Zoom, Discord, Facebook, there is usually something that indicates that a person is online and available for communication. That is essentially what presence information is. It just shows that someone is online and available for communication. The other one requires a little more explanation. We're going to talk about VTC, video teleconferencing. This enables people to communicate via voice and video simultaneously over an IP network. Done with higher quality gear and high-speed networks, VTC simulates face-to-face meetings. Real-time video technologies. So our key goal here is we want to make delays in reception or communication almost imperceivable. These are some common platforms, again, something like Zoom or GoToMeeting. UC network components. So these are the core components: UC devices, UC servers, and UC gateways. UC devices, previously called VoIP telephone, handles voice, video, and more. UC server supports UC services, connects to every UC device. Multiple UC servers may be on separate lanes. So generally, I think the more intuitive thing would be to think that a UC server services just a single LAN, but you can have VC servers separated by a VLAN. A UC gateway, it's just an edge device, maybe a dedicated device or an extra service added to an existing edge router. Router interfaces with a remote gateway and a PSTN system and service. These are some key UC protocols that we need to memorize. H323. This is, according to the textbook, the most commonly used video presentation protocol. It runs on TCP port 1720. So again, it runs on TCP port 1720. Media Gateway Control Protocol, MGCP. Media Gateway Control Protocol, MGCP. Complete VoIP or video presentation connection and session controller. Uses TCP ports 2427 and 2727. VTC and MediaNets. Video teleconferencing can be very sensitive to disruptions and slowdowns. MediaNets are essentially a type of media network or technology that enables rich media communication to work quickly, efficiently, and smoothly overall. So this is the way the textbook describes it: network of routers and servers that provide sufficient bandwidth for a video teleconferencing services. works with UC servers to distribute video conferencing, can be complex or simple. QoS and MediaNets. MediaNets are all about quality of service. VTC needs a very high level of quality of service, as we just talked about before. One of the ways we do that or go about this is something called DiffServ, differentiated service. This is the underlying architecture for QoS. So differentiated service, or DiffServ, is the underlying architecture for QoS. One of the key aspects of this is we add this differentiated service field header on every piece of data. So we add this differentiated service field header to every piece of data. We can see a little image of what that kind of looks like down here. There are a couple key aspects. One is ECN and DSCP. ECN stands for Explicit Congestion Notification, and Differentiated Service Codes Point is DSCP. We'll go ahead and talk a little bit more about what's going on with those in the next slide. So the DSCP is 6 bits and it has 8 classes of service. So we add a class of service to let the field header, and that lets the devices handling this know what priority to apply to that specific piece of data or communication. ECN is a 2-bit field where QoS-aware devices can place a congestion encountered signal to a QoS-aware device. 4 possible values denote the level of congestion and awareness. This is just an image or a screenshot showing managing the 2 settings that we were just talking about. UCaaS, UCaaS. This stands for Unified Communication as a Service. So this is the kind of same concept of unified communication that we were just talking about, but it's usually packaged as some kind of service or cloud service that a company would generally subscribe to and pay for. Here are some examples, something like Zoom or WebEx by Cisco, or maybe something like Microsoft Teams. One of the usually fundamental aspects of these things are something like service integration. And then one of the bigger draws is that you get predictable per user licensing costs. You can also get rid of your in-house communication servers and services, or the team that would normally be responsible for supporting that kind of architecture. And this is just a screenshot of Microsoft Teams management interface showing some user statistics or usage statistics. Okay, up next, ICS. ICS stands for Industrial Control System. It's an overall system that monitors and controls machines. Examples of things to monitor would be things like temperature, power levels, fill quantity, illumination, and all of that sort of stuff. Examples of things to control would be heaters, voltage, pumps, and retractable roofs and valves. So again, we want to emphasize here we're looking at 2 different categories, things to monitor and things to control. In the early days, you would have an operator that is doing most of the kind of stuff manually. They're controlling temperatures, adjusting settings, moving knobs, moving levers, all of this kind of stuff to control the operation of equipments or systems and manage that sort of process manually. Today, a lot of the ICS operators have been replaced by computers or assisted by computer systems. So a lot of this, again, took off when computers combined with digital monitors and controls. So we usually have digital monitors and controls and these smarter systems that will manage or assist the management of our different equipment and machines or systems. Some basic components of an ICS system are inputs and outputs, or input and output functions. So sensors that monitor things like temperature, actuators that make changes that modify the temperature. So again, you have a sensor that'll monitor temperatures, and then you'll have some kind of actuator that is capable of making changes to temperatures on a machine or some kind of system or device. A controller, some sort of computer that manages the process, and the interface for the operator. So just to recap on that, these are our basic components, some sort of input-output function, a controller, and an interface. And this is just an image that may kind of help you visualize what that process is like. Distributed Control System, DCS. In this situation, we have smaller controllers at each machine, and this distributes the computing load. Each local controller connects to a centralized controller. This is just the kind of layout of a DCS system. So again, here we have multiple controllers managing that load, and then they will all connect to a central ICS server. Sometimes you'll hear the term HMI, Human Machine Interface. Early versions were some kind of custom-made box with gauges and switches. Today, we usually have some kind of PC running some sort of custom software or touchscreen interface that we can interact with. Here is a screenshot of that. PLC, Programmable logic controller, computer that controls a machine following a set of ordered steps. A PLC monitors sensors, a PLC controls timing and the order of the process. SCADA is definitely a bigger acronym here. Supervisory Control and Data Acquisition. SCADA, Supervisory Control and Data Acquisition. So that is SCADA. This system is a subset of ICS. It's the same basic components as a DCS, but it's applied to a larger scale. So examples of this would be something like power grids, pipelines, and railroads. In this situation, remote devices may or may not have ongoing communication with the central controller. RTU, Remote Terminal Unit, provides the same function as a controller. The difference is that an RTU has some autonomy if it loses connection with the central controller, uses some form of long-distance communications. So examples would be telephony, fiber optics, and cellular WANs. Network segmentation. Many ICS systems are crucial for the needs of everyday living. So catastrophic failures in these areas can have larger consequences than maybe typical smaller networks. So example, if our electrical infrastructure or something like an oil refinery were to have some kind of issue, the consequences there would be much larger. So we obviously have some reasons to segment our networks. We're going to talk about obviously some of the advantages with that would be things like increased security, optimized performance, reduce network congestion, and limit network problems. Network segmentation in the OSI model. So this is just going to help us picture kind of some of the different ways we can segment a network, kind of using the OSI model to visualize what some of those options might be. So at layer 1, we can physically separate the network from other networks. So some kind of what they call an air gap. At layer 2, we can separate the physically connected network into a separate broadcast domain. We can use things like VLANs. Layer 3, we can also use separate broadcast domains by using different subnets or blocking IP routes. There are some options for above layer 3, which would be things like VPNs, separate SSIDs, separate window domains, and virtualization. All right, that was a fairly quick chapter, but that's all we have for chapter 17 of the textbook. I hope you guys enjoyed the video, and I hope you have a wonderful week. Bye.